Welcome to CEM's Basic Microwave Theory presentation. The purpose of this presentation is to help you become more familiar with basic microwave theory as it applies to organic chemistry. Microwave energy is a form of electromagnetic energy that occupies a region of the electromagnetic spectrum between infrared and radio waves. This means that it has an electric and a magnetic component. The electric component of the wave is the part that interacts with organic molecules and creates heating in reaction mixtures. Due to the fact microwave energy falls between infrared and radio waves on the electromagnetic spectrum, microwave energy does not have the quantum energy necessary to make or break chemical bonds. As shown in this illustration, the energy is only sufficient to affect molecular rotation. If a molecule is exposed to a microwave field and has a dipole moment, then the dipole of the molecule will attempt to align itself with the electric field, which is alternating at the rate of 2.45 gigahertz or 2.45 billion times a second. As the molecules attempt to align themselves with the field, they create heat through friction between neighboring molecules. So microwave energy is not making or breaking chemical bonds, it is simply applying energy directly to the molecules. This chart shows the quantum energy of the 2450 megahertz microwave frequency commonly used. Comparing this value of 0.037 kilocalories per mole to the amount of energy required to break different chemical bonds, you can see that the quantum energy of microwave radiation is orders of magnitude less than energy required even to dissociate a hydrogen bond. There are two mechanisms by which the microwave energy is converted into heat: dipole rotation and ionic conduction. The mechanism of conversion is dependent upon what type of chemical species are present in the reaction mixture that is exposed to microwave radiation. Molecules with a dipole moment transfer microwave energy into heat by attempting to align their dipole with the electric field of the microwave. The movement of these molecules causes heat through friction with neighboring molecules. If there are ions present in a reaction mixture, they will move through the solution in the direction of the electric field, causing heat through friction with molecules it passes. Shown here is the mechanism of dipole rotation as it applies to water molecules. You will notice that the water molecules attempt to align themselves with the oscillating electric field, which causes movements of these molecules, which results in heat. Here you can see ion movement associated with the alternating electric field that also results in the generation of heat. Now let's examine what is happening on more of a macro scale. Because of the ability of microwave energy to directly interact with different species in a reaction mixture, the energy is transferred directly to the components in the reaction mixture. Whereas with conductive heating, the heat must pass through different media such as the reaction vessel and the solvent before the energy is delivered to the reactants. This means that microwave energy is delivered much more directly and rapidly and can be turned on and off very quickly, which allows for some interesting advantages over conventional heating methods. Now that we've talked about the mechanism by which microwave energy is introduced into the system, let's examine how this translates into increased reaction rates and increases in yield. A simple example of an organic reaction is shown here, where A and B are reactants that come together to form C under certain conditions. The equation shown here describes the rate of the reaction. In most cases, the rate of the reaction is a function of the reaction rate constant and the concentrations of the reactants. The reaction rate constant is defined as shown, where A is a factor describing the probability of the reactant molecules to collide in the right orientation for a bond to form. Most people agree that this factor is not influenced significantly by microwave. EA refers to activation energy, which is most likely not affected by microwave radiation. TB and TI refer to bulk temperature and instantaneous temperature. The bulk temperature is the measured temperature of the reaction mixture, and the instantaneous temperature is the temperature that occurs very briefly at the molecular level at certain sites in the reaction mixture as a result of microwave radiation. One of the prevailing theories is that the difference in reaction rates observed for microwave reactions is due to the difference between instantaneous temperatures and bulk temperature. Because the bulk temperature is the observed temperature of the reaction for both conventional and microwave heating, it appears that the reaction mixtures have the same temperature profiles throughout. However, if you use the approximate instantaneous temperature in the reaction rate equation, you can see rate enhancements on the order of those observed in microwave heating. The problem is that these instantaneous temperatures cannot be measured, so it is difficult to show proof of this theory. An interesting exercise to help understand this concept is to back calculate instantaneous temperatures based on reaction rate enhancements. It is generally agreed that microwave energy accelerates reaction rates on the order of 10 to 1,000 times. That would correspond to a microwave K value 10 to 1,000 times greater than the conventional K value for the same reaction. That in turn corresponds to the instantaneous temperatures shown here for a bulk temperature of 150 degrees C. What that says is that for a reaction running at a measured 150 C in a microwave that shows a 10-fold reduction in reaction time over the conventional reaction run at 150 C, that there are instantaneous temperatures around 167 C that drive the reaction to completion faster. And for a 1,000-fold enhancement, temperatures of around 206 C would be present, which is very possible, especially when considering that there may be metal catalysts in the reaction that heat extremely rapidly when exposed to microwave. To expand on this concept, conductive heating and microwave heating can both be viewed as a means of adding energy to a system, thereby increasing the temperature of the system. But in the case of microwave heating, there are instantaneous temperatures that are higher than the measured bulk temperature, which are not present in the conventionally heated system. And the more microwave energy that is applied to a system, the more there is potential for the instantaneous temperatures to be higher in value. This leads to cases where energy is pulled out of the system by cooling the reaction mixture in order to apply more microwave energy in order to drive the reaction. This also helps explain why microwave energy not only speeds up reactions, but also shows greater yields and better selectivity. Microwave energy can apply a high level of energy to a system to push a transformation to occur without creating a high level of bulk heating, which can cause decomposition or lower selectivity product formations. Having the benefit of both these scenarios simultaneously can yield better results, sometimes even allowing reactions to occur that do not occur without microwave. And these results sometimes cause people to speculate that something unexplained is happening with microwave. To summarize, microwave is a tool for adding energy to a reaction mixture much the same as a hot plate, but it allows a much more efficient transfer of energy. And not just for high temperature reactions, but for reactions run at all temperatures. Some of the major advantages of microwave as it relates to organic chemistry are: 1. It dramatically reduces reaction times. Reactions that typically take hours or days can be reduced to seconds or minutes with the microwave. 2. It can increase the yield or selectivity, sometimes dramatically, of reactions. It is not atypical to see a 20 to 40% increase in yield and to see greater than 90% selectivity towards a certain product where conventionally there is very little or no selectivity. Microwave has also been shown to yield reasonable amounts of product for reactions that when run conventionally yield almost no product. So microwave allows a chemist to reduce the number of steps in a total synthesis, reduce or eliminate the amount of purification needed, and gives access to molecules that previously were inaccessible, giving way to the term microwave compounds. Another benefit of microwave is that it allows the use of more benign solvents, like water, and even opens the door to a lot of neat reactions that eliminate the need to use a solvent at all. Hopefully this tutorial has helped you better understand how a microwave system works and how it can be used to enhance organic chemistry. The best way to familiarize yourself with microwave is to try it. It's easy to use and will bring benefit to any type of reaction you're running. And as always, our staff of chemists can always be contacted to discuss microwave chemistry.